Homogeneous second-order linear differential equations. So any equation that's second order and linear with constant coefficients can be put into the form a number a times y prime prime plus a number b times y prime plus a number, that's c, times y equals 0. So the homogeneous is the equals 0 part. So homogeneous differential equations are linear combinations, or homogeneous linear differential equations are linear combinations of the derivatives equals a number equals 0. So they're all the same. These homogeneous second order constant coefficient linear differential equations, they're all the same except for you pick different numbers a, b, c. They're all of this form. Now, to see how to solve this, let's take our inspiration from something we know. Here's a first order linear constant coefficient differential equation. But I can see that I can rearrange this to be y prime is equal to 2/3 y. So basically we've got a rate proportional to the amount present. So it's exponential growth or decay. It's growth in this case because the constant here 2/3 is positive. So we have our solution. A constant y is equal to a constant e to the 2/3 t. How do I get this constant? Initial conditions. In fact, we know this constant is going to be y naught. This constant c is going to be equal to what the value of y is when time is equal to 0. So we're getting a solution of this form. Y is equal to some constant e to some number times t. And the sum number is connected to the 2 and the 3 here. So the sum number, the 2/3, the lambda in this case, is connected to the differential equation. The constant is connected to the initial condition. In this case, is the initial condition. So let's take this idea, that solutions are of this form, and go back to our second order linear constant coefficient. If I propose solutions of this form, well, I can sub this into the left hand side here, and in order to do that I'm going to need y prime. So if I'm going to sub this solution into the left hand side and make it equal to 0, figure out what c and lambda have to be so that that form is a solution. I'm going to need the first derivative and the second derivative. Let's pop it into the left hand side and make it equal to 0. So that would be a times y prime prime plus b times y prime plus little c times c either. So there's big C and little c, and set it equal to 0. And now we just have to figure out what c and lambda have to be. Well, notice I can factor this side. When I factor it, I get e to the lambda t times c times this backwards quadratic. Let's fix that. Alright, so this equation has to be, well, I've got three things multiplied together to give me 0. The e to the lambda t, that can't be 0. The c, I'm about to say that can't be 0. I guess it could be 0, we don't know yet, but if it was 0, then the solution would be 0, its derivative would be 0, the second derivative would be 0, everything would be 0. So it could happen, but then your initial conditions would have to be y equals 0 and y prime equals 0 at t equals 0. Before we continue, let's take care of this then. We're solving a second order differential equation. So I should have two constants. Solving this second order equation is akin to integrating twice. So I should have two constants in the end, and that means I'll get to have two conditions. I'll get to have a y naught and a y prime naught that I can sub in. Anyway, so the c, none of these pieces can be equal to 0, so I guess the only option for solving this is if this a lambda squared plus b lambda plus c is equal to 0. So this is what we're going to call then the auxiliary equation. Now, how did we get the auxiliary equation? Well, we got it by substituting in this c e to the lambda t, factoring out this capital C, factoring out the e to the lambda t, and then getting this quadratic in terms of lambda equal to 0. There's our auxiliary equation. But notice, where it's prime prime, a y prime prime, it's lambda squared. Where it's 1 prime, it's 1 lambda. Where it's no prime, it's no lambda. So I can, in the end, go from the differential equation, the homogeneous second order linear differential equation, and I will at the end of solving a few of these be able to just straight write down the auxiliary equation, where the number of primes is equal to the number or the power of the lambda. So anyway, we have to solve this for lambda. It's a quadratic, so I know I'm going to get two solutions. Well, okay, I could get two real and different solutions, I could get two real and the same solutions, or maybe I get lambda equal to a complex conjugate pair, but in the end I get two solutions. Let's jump to an example now so we can just see it working. Here's one. Y prime prime plus 5y prime plus 6y equals 0. For pedagogical purposes, let's sub in the y equals some constant e to the lambda t. We'll need all of these derivatives here. Let's just put this down. So I would substitute these in this equation, then factor out the c, factor out the lambda, and then I would end up getting lambda squared where the y prime prime is. So now I'm going to ask you to do this on your own, in the comfort of your own home. That would be plus 5 lambda plus 6 equals 0. And this one I can factor. I'll get lambda plus 2 times lambda plus 3. So I get two answers then. I get either lambda equals minus 2 or lambda equals minus 3. So here's my solutions then. That means, remember I proposed a solution of this form. Let's put this up front here. That means I get, well, I guess I get two solutions here. First I get one, so let's label them 1 and 2. I get one solution that would be e to the minus 2, some constant e to the minus 2t, and I get some other solution, a separate solution, a second solution, that would be some constant e to the minus 3t. They both, and again I'm going to ask you to check this, they both solve this differential equation. So what am I going to do? Oh, and do I know if these constants are the same? I guess I don't, so I'm going to label them 1 and 2 because I'm not sure. In fact, I have got no information on these constants at all. The differential equation did give me information on what the lambdas have to be, or what the lambda could be for a solution of this form, minus 2 or minus 3. It's given me maybe too much information. But let's think about what we really have here. We've got a linear second order differential equation. I'm going to have two initial conditions that I can invoke here. And I guess, well, let's put some initial conditions in here, since I get to pick some. Let's pick y naught equals 1. Oh, if y naught's equal to 1, then whether I use y1 as my solution or y2 as my solution, that tells me that c1 has to equal to 1 and c2 has to equal 1. They both have to equal 1. Okay, I get another condition. The slope, let's say, is equal to 0. So this is basically saying that the solution to this differential equation goes through the point 0, 1 with a slope of 0. It goes through the point 0, 1 flat. Problem. This initial condition can be solved for both y1 and y2 if the c's are 1. This initial condition can be solved for y1 and y2 if both the c's are 0. But I need to be able to satisfy both of these. Each c can't do the job of satisfying the initial conditions on their own. Long story short, what we're going to do then is, and I'm going to call this sub h for homogeneous, the solution to this homogeneous equation, is I'm going to just add these two solutions together. And call this the solution. Now, there's two things, I guess. First off, I know that this little piece, I know this c1 e to the lambda 2 is a solution to this differential equation. I checked it. You were supposed to check it as well. I know that this c2 with the e to the minus 3 is also a solution. If I add them together, I have to show you that that's also a solution. I'm going to ask you to verify that this sum of two solutions in this particular example is also a solution. So you're going to differentiate this once, you're going to differentiate this twice, you're going to have your y prime, your y sub h, your y sub h prime, your y sub h prime prime. You're going to substitute it in this left side and see that everything cancels out and gets 0. So in this case anyway, you'll prove to yourself that the sum of those two solutions is also a solution. What about the constants? Well, this first y0 is equal to 1 gives me the equation. If I make my t equal to 0 and set the y homogeneous equal or homogeneous equal to 1, then I get that the sum of the two, so here's me setting t equal to 0, e to the 0 is 1. I get an equation for c1 and c2. They both have to add to be 1. And if I differentiate this, and then invoke the second initial condition that the derivative at 0 has to be 0, here I end up getting then two equations, two unknowns. So before, when I was trying to just use one, like a y1 as the solution or a y2 as a solution, separately, not together, ended up with a problem because I had one constant trying to do two jobs, trying to satisfy both initial conditions. Now, when I add them together, my motivation for doing that is I get to have both constants in the solution. So I've got two conditions and I've got two constants to dial in and solve for those two conditions. When I invoke those two conditions, I end up getting two equations, two unknowns, so I can solve for C1 and C2. So I solved these two equations by elimination. These two equations by elimination, you could use substitution, whatever, or Kramer's rule if you want to get all linear algebra-y on it. Anything that's available, you solving these two equations, two unknowns, and I get these two C's. I get C1 equals 3 and C2 equals minus 2. So now I've got a solution to the differential equation. Now I've got a solution that satisfies both initial conditions and satisfies the differential equation. As far as existence and uniqueness, well, existence, there it is. Uniqueness, I only had one choice for the C's. And I had two choices for the lambda, but I had to add them together in order to get the two C's in order to satisfy the two initial conditions. So, in general then, let's show this in general. In general, any two linear combinations to a linear second order constant coefficient homogeneous differential equation is also a solution. So in order to show that, I need to have, well, I need to start off with my assumption. So say, now I'm going to end up writing y1 and y2, but they're just any general solutions. So they say these two equations solve my ay prime prime. So in other words, if I sub y1 in the left side, I get 0. If I solve y2 in the left side, I get 0. So now I want to show that a solution that's just y is equal to y1 plus y2. Oh no, that's the sum. I want to show any linear combination. So some constant. So a linear combination of these two solutions will also be a solution for any of the constants. So in order to show that this solves this, I need to get the first derivative, sub it in here, the second derivative, sub it in here, the original y, sub it in here. So I need the derivatives. Because it's linear, the derivatives, y prime is just going to be y1 prime, y2 prime, and the second derivative so I need to sub these three pieces in this left-hand side and make it equal to 0. That's going to be a times y prime prime plus b times y prime plus little c times y and I want to show that that equals 0. I'm not going to make it equal to 0 yet. I have to go through some algebra and show that. Well, the algebra is going to be then collect all your y1s and all your y2s. Now I'm going to collect on all the y1s and collect on all the y2s, and in that case, when I do that, I'm going to get c1 times, it's easier for me to do this, which equals, over. Well, since y1 solves this differential equation, this expression must be equal to 0, and since y2 also solves this differential equation, then this bracket has to equal to 0, so it'll be c1 times 0 plus c2 times 0, I don't need that other line, the whole thing equals 0, and then what have we shown? Any linear combinations, any linear combination of two solutions is also a solution to the general equation. So the thing we did back here, where combining two solutions together, two little solutions, the y1 and y2, that's good, that's okay, that always works. Why would I want to do that? Well, by combining the two solutions together, we get two constants in the one solution. So I could hit two, I could satisfy two of the initial conditions, the y naught and the y prime naught. Notice, let's go back up to our differential equation here. The initial conditions gave us the constants. The differential equation gave us the lambdas, the eigenvalues, the roots of the characteristic equation, or roots of the auxiliary equation, if you will. I can call this the characteristic equation or the auxiliary equation. The eigenvalues are the lambda. Eigen is just German for characteristic. So saying characteristic values or saying eigenvalues is the same thing. Let's go through, let's solve an equation now. Let's just do an example. All right. Well, what's my first thing? Let's throw down our auxiliary equation. I can factor this auxiliary equation, think. And so I get lambda equals 4 or minus 3. So I get two little solutions then. I get a little solution e to the 4t, and I get little solution e to the minus 3t. Now I'm not putting constants in front of them. I guess I can, but I'm not going to, because I'm going to take a linear combination of these two pieces anyway. I'm going to say my homogeneous solution is equal to some constant times the e to the 4t plus some constant e to the minus 3t. So I'm labeling these constants right now C1 and C2. How do I find these constants? Initial conditions. That's how I find the constants. So here's my solution. All I need are the C's, and I'm going to find those by the initial conditions. If I make t equal to 0, y is equal to 0, that gives me the equation 0 equals C1 plus C2. And if I take the derivative, I'm going to get 4. 4 is going to come down. If I take the derivative of this, let's differentiate this. That'll be I'm differentiating with respect to t. So a 4 comes down and a minus 3 comes down. If I invoke the second condition, that y prime naught is equal to 7, that means 7 is equal to So now I've got two equations, two unknowns. I can solve this by substitution, elimination. Let's solve this by substitution. So if C1 plus C2 is equal to 0, I can say that C1 is equal to minus C2. So I can substitute that in the second equation and get 7 equals 4 times, instead of C1, I'm writing minus C2 minus 3 C2. So it looks like 7 is equal to minus 7 C2. So C2 must equal minus 1. If C2 is equal to minus 1, then C1 is equal to 1. So now I can write my solution with the constants in it. C1 is equal to 1 and C2 is equal to minus 1. If I were to sub in t equal to 0, I get 0. If I'm differentiating this and then sub in 0, I get 7. I know this solves the differential equation because it has the correct eigenvalues. It's now a linear combination of the e to the proper eigenvalues t. How does that sit with you? Existence and uniqueness. Well, the existence and uniqueness, let's look at the uniqueness. Once we start to invoke the initial conditions, that's when I get the unique constants. The differential equations part, the y prime prime part, the actual differential equation part gives me the lambdas, gives me the eigenvalues. The initial conditions give me the c's. Let's do another couple of examples here. Find the solution, the general solution to the problem. Well, now this starts to be more straightforward, right? I look at this. First off, there are no initial conditions given. So that means I can't find the C's. I don't have to find the C's. I just need the auxiliary equation. I need to factor the auxiliary equation or use the quadratic equation to solve the auxiliary equation. In this case, I think I can just factor it, and I'm getting lambda plus 3 times lambda plus 4 equals 0. So lambda equals -3 and -4 as solutions to this auxiliary equation. So now I can just straight write down the solution. The homogeneous solution is equal to some constant e to the -3t, there's the first solution, plus some constant e to the -4t. Done. We've solved this differential equation. I can't find the c's because we don't have the constants. Now a question. What's the relation between the signs of the eigenvalues of the lambda and the limit as t approaches infinity of the solutions? Well, they're all these solutions so far are all e to the eigenvalue, e to the lambda t. So if that eigenvalue is negative, then this solution goes to 0. If that eigenvalue is positive, then this solution goes to infinity, or I guess minus infinity if the constant in front of is negative. But let's look at the 3 examples we solved. This one, eigenvalues negative, eigenvalues negative. So when I have a linear combination of those 2 pieces with the negative eigenvalue, as t goes to infinity, this piece goes to 0 and this piece goes to 0. So the homogeneous solution goes to 0 because both eigenvalues are negative. In this next example, we've got a linear combination of e to the 4t and e to the -3t. As t goes to infinity, e to the -3t, that does go to 0. But this e to the 4t goes to infinity or minus infinity depending on what c1 is. It happens to be 1 in this case, so the solution goes to infinity. Yeah, this piece goes to 0, but the other piece doesn't. Here we've got both negative eigenvalues, so both pieces go to 0. So I guess what's the relationship between the signs of the eigenvalue and the limit as time goes to infinity, or what the solution eventually approaches? This is either equal to 0 if both eigenvalues are negative. Or else it goes to infinity. And yeah, I guess if we want to be perfect here, it'll be like plus or minus infinity. But it's unbounded. So the homogeneous solution, as t approaches infinity, the homogeneous solution always eventually goes to either 0 if both eigenvalues are negative, or infinity if both of them are positive or if one of them is positive. So now we can now solve equations of this form, homogeneous second order linear differential equations. We can solve these equations. We get the auxiliary equation, we factor the auxiliary equation or use the quadratic equation to solve it, get the 2 lambdas, make our homogeneous solution a linear combination of the 2 little solutions, the 2 e to the lambda t's. If initial conditions are given, we can figure out what the c's are, and I guess we're done. Of course, there's more videos on this topic. We're not done. We're done if we solve the auxiliary equation and we get 2 real and different roots. Then we're done. I guess what happens if I get 2 real and the same roots, because that could happen if I solve this quadratic equation in lambda, or the more exciting idea is, what if I get complex eigenvalues? What if this quadratic equation in lambda doesn't have real roots? Then what do we do? Well, we watch the next videos and find out.